Successive transformations, revision of the basics. Y is equal to sine x, where x is in degrees. Let's apply a translation in the positive x direction by 45 degrees. So replace x with x minus 45. So we get y is equal to sine x minus 45. The graph of y equals sine x, and we're going to move the graph to the right by 45 degrees. In function notation, y is equal to f of x becomes y is equal to f of x minus 45. Example 2, a translation in the negative x direction by 60 degrees. Replace the x with x plus 60. So we have y is equal to sine x plus 60. So y is equal to sine x. The graph moves to the left by 60 degrees. So we have the graph of y equals sine x plus 60. Example 3, y is equal to sine x, a translation in the positive y direction by 2 units. So we just add 2 on to the original equation. So the graph of y equals sine x will move up by 2 units. This graph has a minimum at minus 1 and a maximum at 1. After the transformation, the minimum will be minus 1 plus 2, and the maximum will be 1 plus 2. The minimum is now 1 and the maximum is now 3 for y is equal to 2 plus sine x. Example 4, a reflection in the x-axis. In this case, you change the signs on one side of the equation, so y equals sine x becomes y is equal to minus sine x. So this graph, y equals sine x, will be reflected in the x-axis to give y is equal to minus sine x. Example 5, a reflection in the y-axis. So in the equation you replace the x with minus x to get y is equal to sine minus x. So the graph of y equals sine x will be reflected in the y-axis to get the graph of y equals sine minus x. So this is the reflected graph in the y-axis. Example 6, a stretch in the x direction, so parallel to the x-axis, by a scale factor of 3. So replace the x in the original equation with x divided by the scale factor. So replace the x with x over 3 to get y is equal to sine x over 3. So y is equal to sine x will be stretched by a scale factor of 3 in the x direction. Point A on the graph has an x-coordinate of 90 and a y-coordinate of 1. After the stretch in the x direction, the x-coordinate will be multiplied by the stretch factor and the y-coordinate will remain unchanged. So this is the graph of y is equal to sine x over 3 after the stretch of times 3 has been applied in the x direction. And here is point A, and the x-coordinate is now 270, so 3 times the original x-coordinate, and the y-coordinate is unchanged. Example 7, a stretch in the x direction by a scale factor of a half. So this time we're going to replace x in the original equation with x divided by the stretch factor of a half, and x divided by a half can be simplified to 2x. So we replace the x in the original equation with 2x. So we get y is equal to sine 2x. So the graph of y is equal to sine x, when stretched by a scale factor of a half in the x direction, will result in all of the x-coordinates on the original graph being multiplied by a half. So for instance, this point here, let's call this point A, it has an x-coordinate of 180, and the y-coordinate is 0. So after this stretch has been applied, this point will be at 90, half of 180, 90, 0. So this is point A after the stretch, and the x-coordinate is now 90. The y-coordinates are unchanged. Example 8, a stretch in the y direction, scale factor 2. So this time we're just multiplying the original equation, so the sine x, by the scale factor. So y is equal to sine x will be stretched by times 2 in the y direction to give y is equal to 2 sine x. So this graph has a maximum of 2 and a minimum of minus 2. So the y-coordinates have been multiplied by 2. The x-coordinates are unchanged. So as an example, point A on the original y equals sine x graph has coordinates 90, 1, and after a stretch of times 2 in the y direction, the x-coordinate will remain the same and the y-coordinate will be multiplied by the stretch factor. So that 1 becomes 2, 1 times 2. So here is point A after the stretch in the y direction by times 2.